Hi everyone, I'm Zhang, a PhD student from University of Rochester. Today I'm going to present my paper, A Probabilistic Framework for Spoofing Aware Speaker Verification. For this task, it is a joint system combining the automatic speaker verification and anti-spoofing. For anti-spoofing system, or spoofing aware countermeasure, it aims to discriminate the bona fide speech and spoofed speech, where bona fide speech means natural speech from human being, and spoofed speech are generated from text-to-speech and voice conversion algorithms. For ASV system, it aims to discriminate whether the test utterance is from the target person. But research has shown that ASV systems are vulnerable to spoofing attacks. The SASV system aims to use any spoofing system to strengthen the speaker verification parts. So only if the test utterance is bona fide speech and also from the target speaker, the utterance is considered as positive class. Otherwise, it is negative class. So SASV is still a binary classification problem. For existing methods, there are mainly two kinds of methods. The first one is multitask learning-based method, but it requires both speaker and spoofing labels. So currently, only ASV spoof datasets can support this, but it has a limited number of speakers. So this joint system might overfit the thin speakers. Another one is fusion-based methods. We can do score level fusion or embedding level fusion. And these two subsystems can be trained on different datasets. This year, the SASV challenge was held. Previously, due to the lack of standard metrics and datasets, it is hard to benchmark the state-of-the-art spoofing-aware speaker verification system. The challenge used the ASV Spoof 2019 LA datasets, which includes different speakers and different kinds of spoofing attacks. But all of these attacks are text-to-speech and voice conversion algorithms. And for each test trial, they provide multiple corresponding enrollment utterances. And also they list the target, non-target, and spoof trials. They also standardize the evaluation metrics for this spoofing-aware speaker verification task. So for each test utterance, it either belongs to target, non-target, or spoof class, where the target class means that the utterance is from the target person. Non-target means the utterance is not from the target person. And both target and non-target class should from the bona fide speech. And the spoof class means that the utterance is from spoofing attacks. The metrics are basically ER equal error rates, where the false alarm is equal to the miss rate. So it is a standard metric for binary classification. The SASV ER consider the target as positive class, and both non-target and spoof are negative classes. SVER consider only target and non-target, and spoof ER consider target and spoof. So note that this spoof ER is still different from the ER metric for anti-spoofing, because the anti-spoofing consider both target and non-target as positive class. They also provide different baseline methods, and I will introduce in next slides. So the baseline methods are all fusion-based methods. Baseline 1 is score level fusion, and baseline 2 is embedding level fusion. For the two subsystems, the ASV subsystem, they use the ICAPA TDNN method, and they are pre-trained on VoxLab2 dataset. And for the anti-spoofing subsystem, they use the AASIST and also pre-trained on ASV Spoof 2019 dataset. So the enrollment utterance will go through this ICAPA TDNN system and provide the speaker embedding for the enrollment utterance. For the test utterance, it will first go through the ICAPA TDNN to provide the speaker embedding, and also go through the AASIST model to provide the CM embedding. So there are three embeddings here, and all of these embeddings are pre-trained and fixed. In the next stage, baseline 1 method first calculate the cosine similarity between the two speaker embeddings. So this is the ASV score. And for the anti-spoofing parts, the CM embedding goes through the FC layer to provide the CM score. So note that this FC layer is also from the AASIST model. So this is also pre-trained and fixed in baseline 1. And after they provide the ASV score and CM score, these two scores are added. So the final SASV score is the summation of ASV score and CM score. For baseline 2, it is an embedding level fusion. So these three embeddings are concatenated. The concatenated embedding is fitted into another deep neural network, and this deep neural network will predict the SASV score. So this final SASV score is used to discriminate the positive class and negative class. And we first perform a score distribution analysis on the baseline systems. So before that, we plot the histogram for the separate systems or the subsystems. For the ICAPA TDM method, we can see that it can successfully discriminate the target and non-target class, but the spoof class has a lot of overlap with the target and non-target class. This shows that the ASV system is vulnerable to spoofing attacks. And for the AASIST model, we can show that it can successfully discriminate the spoofing attacks from the target and non-target, but the target and non-target class has a lot of overlap. This is because the anti-spoofing model is trained to discriminate spoofing attacks, but both the target and non-target are bona fide speech. And for the baseline 1 and baseline 2 method, we also plot the histogram of the score distribution. We find that the score distribution of baseline 1 method is very similar to the AASIST model. The only difference is that the target class is deviated by some distance. And if we look at the range of the previous separate systems, we find that the ICAPA TDM method, the range is from -1 to 1. This is because the ASV will output the cosine similarity, but the ASS is directly using the output from the FC layer. So by adding these two scores together, the final score of baseline 1 is dominated by the CM system. And for baseline 2, it is an embedding level fusion method, and we can see that it has better performance. In our work, we propose a probabilistic fusion framework, where our method also takes the three embeddings, where XEASV means the ASV embedding from the enrollment utterance, and XASVT means the ASV embedding from the test utterance, and XCMT means the CM embedding from the test utterance. So these three embeddings are exactly the same as the baseline systems. So these three embeddings will be taken into our system, and we make the joint decision YT, where if YT equals to 1 means that it is positive class. So the utterance is bona fide speech and also from the target person. And if YT equals to 0, it means it's either non-target or spoof. So we assume that there are some hidden states between the embedding and the joint decision. We call it subsystem decisions. So the XASV E and XASVT will determine the YASVT. So this is to decide whether the test utterance is from the target speaker. So if it is from the target speaker, then YASVT equals to 1. And if not, YASVT will equal to 0. And similarly, the YCMT is used to determine whether the test utterance is bona fide speech. If it is bona fide speech, YCMT equals to 1. If not, YCMT equals to 0. So based on this graphical model, we can derive the formula from the product rule. So finally, we need to predict the probability of YT equals to 1 given these three embeddings. And only if these two subdivisions should be equals to 1 or should be positive. So the first equality is by the definition of the spoofing aware speaker verification. And the second equality is based on the conditional independence that we assume the ASV subsystem is independent from the CM system. The last equality is based on the graphical model that the ASV part is only dependent on the speaker embeddings, and the CM part is only dependent on the CM embedding. So based on this probabilistic fusion framework, we propose different strategies. So first, we use the direct inference strategy were implemented as the right figure. So previously, the baseline method output the score of ASV and the score of CM, but this is different from the probability. So in our work, we map these two scores to the range of probability. And for the CM score, because it is previously pre-trained with the softmax loss, so if we apply a sigmoid function, it is natural to be the probability of whether it belongs to the bona fide speech. And for the ASV score, it is previously the cosine similarity, which is in the range of -1 to 1. So we apply score mapping to map the score to the range of 0 to 1. And after mapping these two scores to the probability based on the previous product rule, we use the final SASV score as the multiplication of these two mapped scores. So this is the direct inference strategy. And for the fine-tuning strategy, we no longer assume that the ASV subsystem is independent from the CM subsystem because we want to fine-tune the two systems. So now the second equality is not based on conditional independence, it's directly based on the chain rule. So here we can find that the CM system is based on ASV system. We implemented this by setting the FC layer to be trainable, and we retrained the FC layer by optimizing the final SASV score based on the cross-entropy loss. So the gradient is back-propagated into this FC layer, and we can find that this gradient is weighted based on the ASV score. And the gradient received the larger weights for larger ASV score, which corresponds to utterance that are more similar to the target speaker. So this helps the model to pay more attention to difficult samples, manifesting an idea of speaker-aware anti-spoofing. For the results parts, we show that our methods based on product rule have better performance than the baseline methods. So here, L, S, and C are different mapping methods, where L is linear mapping, S is sigmoid mapping, and C is score calibration with logistic regression. And this I and F are different strategies. I means the direct inference strategy, and F is the fine-tuning strategy. So we find that the fine-tuning strategy is also better than the direct inference strategy. Our best performing system, TRSF, achieves 1.53% SASV ER on the evaluation set. And finally, we perform the score distribution analysis on our best performing system, and we show that our system can successfully discriminate these three classes: target, non-target, and spoof. It's much better than the baseline methods. Also, we perform ablation study. Our system, PRSF, achieved the best performance. And if we remove the fine-tuning strategy, we use direct inference, the performance got degraded. So this shows that the effectiveness of our fine-tuning strategy. And from the PRSI, so this is similar to the baseline one method, because the baseline one method is also a direct inference method. So the only difference is that we applied both score mapping and score multiplication based on our probabilistic framework. So if we restore the multiplication to sum, the performance also degraded. And if we only remove the score mapping, where the system is now baseline one plus score multiplication, the performance is also degraded. And if we restore both, the system will become baseline one. And on the right, we plot the score distribution for these two systems. And we show that the score mapping and score multiplication are both useful, but the performance is not as good as our. So finally, our conclusion is that our proposed probabilistic framework is effective to spoofing aware speaker verification. And with the product rule and fine-tuning strategy, we achieved 1.53% SASV ER, which significantly improved the baseline methods. Our full paper and code and challenge summation are available in these links. Thank you, everyone. If you have any questions, feel free to reach out to me. Thank you.